Hola a todos, bienvenidos. Vamos a dar comienzo a esta conferencia magistral para que no nos perdamos ni un minuto de la presencia de Douglas aquí en Chile. Así que, para los que no saben, esta conferencia se enmarca en el ciclo de conferencias magistrales que está impulsando la Vicerrectoría Académica. Y para eso tenemos a Manuel Villalón, acá el director académico de docencia, que nos va a contar un poco la motivación de estas conferencias magistrales. Así que adelante, gracias.
Bueno, antes que nada, gracias a Douglas por estar aquí y a todos ustedes por esta importante audiencia. La Vicerrectoría ha estado trabajando en este ciclo de conferencias magistrales que lo que propone es acercar el desarrollo de las disciplinas, invitados que las disciplinas tienen, pero que una audiencia más amplia tenga la oportunidad de conocer qué es lo que se está haciendo, cómo el mundo está cambiando en esta respectiva disciplina y contribuir de esta manera a la formación integral de nuestros alumnos. Creemos, hay varios ciclos, otras conferencias. Yo les pediría, por favor, que ustedes son los mejores agentes para contribuir a la difusión de estas actividades. Queremos que esta universidad sea un espacio donde las disciplinas nos encontramos, conocemos cuáles son sus preocupaciones, conocemos cuáles son sus desafíos, y en este caso en particular conoceremos la experiencia de un físico que llegó a otras áreas, y eso es un poco lo que nos interesaría que alumnos también pensaran, que uno entró tal vez a obtener un título en particular, pero que este fue una experiencia de vida importante y que los puede llevar a experimentar o trabajar en otras disciplinas. Entonces, con esta motivación y con este mensaje, vuelvo a reiterar mis agradecimientos a Douglas por la oportunidad que nos da de conocer esta conferencia magistral. Gracias.
Bueno, y yo les voy a contar un poco que hoy día vamos a tener una exposición de 50 minutos de Douglas, y luego vamos a tener un break de 2 a 2 y cuarto para que quienes tengan que ir a clases o quienes tengan programada otra actividad puedan retirarse de la sala sin que metamos mucho ruido. Y a las 2 y cuarto vamos a retomar con una sesión de preguntas y respuestas. ¿Ya? A todos se les entregó un papel en la entrada en la cual pueden hacer sus preguntas, y nosotros en esos 15 minutos las vamos a recoger y las vamos a tomar en cuenta para la conversación que venga a las 2 y cuarto. ¿Ya? Así que disfruten. Los dejo con Francisco Claro. Francisco Claro va a hacer la presentación de nuestro invitado.
Muchas gracias. Para que no se me olvide nada, traje un papelito. Bueno, Doug, como han visto en los afiches, es profesor de ciencia cognitiva. Es profesor de ciencia cognitiva y literatura comparada en la Universidad de Indiana. Es fellow de la Academia de Arte y Ciencia de Estados Unidos, es miembro de la Royal Society of Science de Uppsala, en Suecia. Él es conocido especialmente por su libro Gödel, Eschenbach, An Eternal Golden Braid, un libro cuya génesis se sitúa, sus raíces se sitúa cuando Doug hacía un trabajo de doctorado en la Universidad de Oregon. Este libro, que salió, diría yo, de sus entrañas, creció como un árbol así, misterioso, que se apoderó de él por un tiempo. También se ha apoderado de miles de personas, ha sido traducido a numerosos idiomas, ha vendido millones de ejemplares, ha sido realmente un libro que ha acercado a Doug mucho, y su mensaje lo ha acercado a la comunidad internacional. Tiene premios, tiene el premio Pulitzer, que es el premio más importante en Estados Unidos a obras literarias y de ensayos. Tiene el National Book Award también de Estados Unidos, que también es muy prestigiado. Y Doug ha, por supuesto, continuado su búsqueda y ha publicado una cantidad de libros, uno de los cuales también, recuerdo, tiene un premio en Los Ángeles, del Los Angeles Times Book Award. El libro se llama I Am a Strange Loop. Es un título muy cautivante y que refleja mucho lo que Doug expresa, lo que las ideas de Doug muestran también. Ahora, yo otro libro que quisiera mencionar, por ejemplo, un libro que es poco conocido acá porque se publicó en italiano, que se llama Ambigrami, Dag ha tenido siempre una fascinación por el diseño, por la forma, por la cosa visual y en el lenguaje. Y ambigrami es un estudio de algunos objetos, yo llamaría, de diseño que envuelven simetrías y que Dag ha hecho desde que era niño. Entonces, esta es una especie de reflexión de esta creación de Dag, que él llamó también ambigrami. Otra faceta de Dag, este hombre multidisciplinar que tenemos acá, es que tradujo del ruso una de las obras cumbres de la literatura rusa, Evgen Onegin, que escribió Pushkin, y esto lo hizo Dag en medio de un aprendizaje él mismo del idioma ruso, que llegó a la cumbre, digamos, de poder traducir un poema que es muy querido por el pueblo ruso y que él quería justamente hacerle también un homenaje, tanto al libro como al autor. Yo personalmente lo conozco desde que éramos compañeros de estudio, como estudiantes graduados. Conozco muchos aspectos de su vida y también de su creación. Y quería mencionar en la creación el único trabajo de física que publicó. Generalmente a uno le piden que trabaje que escriba por lo menos un par de artículos al año, pero Dag escribió solamente un artículo. La diferencia con nosotros es que este artículo de Dag tiene más de 2000 citas. O sea, es un artículo que rompió fronteras realmente. Y que dio lugar incluso a un nombre que se llama The Hofstadter Butterfly y que vuela por todas las naciones y que realmente es un objeto muy bonito estéticamente. Lo que produce, no voy a hablar de eso, pero además es muy inspirador y hay mucha gente que lo conoce y reconoce su valor como ciencia. Ahora, si yo me pregunto qué es lo que nos unió a Dag como estudiantes, en fin, éramos muchos estudiantes, y por qué nosotros nos hicimos amigos, y yo creo que, por un lado, es la apertura de Dag a lo internacional. Yo venía de un país pequeño, que a lo mejor mucha gente no conoce ya, entonces eso ya es atractivo para él, otro idioma es atractivo para él, pero en lo que resonamos particularmente, aparte de nuestro interés en la física, es nuestra profunda devoción por la música. Y nos encontrábamos no solo en el departamento de física, donde teníamos largas conversaciones, sino que también en el departamento de música. Lo conozco también por compartir mucho del humor. El humor es muy importante para Dag. Las conversaciones con Dag no son serias. Yo creo que nunca he podido tener una conversación seria con él, porque siempre, después de la segunda palabra, empieza a funcionar el sentido del humor y la broma. La otra cosa que nos une es una fascinación por el lenguaje y por el lenguaje en sus aspectos no solamente de contenido, sino que también de visuales, de forma. Cuando converso con Dag trato de enhebrar alguna cosa profunda, entonces me corrige el lenguaje. Yo estoy hablando de cosas íntimas a lo mejor y me corrige una frase porque la dije mal. Eso es muy típico de él, pero también la ambigüedad en el lenguaje es una fascinación de ambos y que nos lleva mucho al territorio del juego de palabras. Y por ejemplo, cuando veníamos en el auto, todo el viaje en el auto hacia acá fue un puro juego de palabras. Y eso es lo normal en nuestra relación. Así que tenemos ante nosotros un hombre verdaderamente multidimensional que yo personalmente quiero y aprecio mucho y que le agradezco que haya venido. Con ustedes, Douglas Hofstadter.
Buenos días a todos. Yo no voy a hablar en español, pero quisiera empezar mi conferencia en español o en castellano, es mejor decir castellano, no sé. Sería muy difícil para mí tener una conferencia en español porque tengo muchos agujeros en mi vocabulario. Y además, este sujeto es muy complicado y muy especializado y por eso yo voy a cambiar en mi lengua materna, pero querría por lo menos empezar en español. Gracias por esto. And now a little bit of a switch in language. So let's see my notes. And my glasses and my watch, so I know what time it is. Okay. When I was a graduate student with Francisco Claro in Oregon in physics, I was fascinated. Every time I went to a colloquium, I was fascinated by the physics itself, the ideas, which were very beautiful, magical, but I was particularly interested also in the pathways of discovery. How did a physicist discover a new idea? Usually they didn't talk about that very much. They didn't explain how they came to new ideas. But once in a while they would give an analogy that in the middle of the talk they would say, "Excuse me now, I will make a little analogy." And then they would give an analogy that made the ideas very clear. Even if they were technical and difficult, the analogy would often make it very clear. And you could see that the essence of their own thinking had been that analogy, but they were ashamed to talk about it. They didn't want to talk about analogies. They wanted to make it seem as if physics was purely logical and always deductions and manipulations of equations and such things. That's safe territory. If you go into the territory of analogy making, everybody knows that analogies can be misleading, they're approximate, you can't rely on them always, and so they don't talk about them. They tend to avoid them, except as sort of humorous or, you know. But the truth of the matter is that deep thinking comes from analogies. Also, shallow thinking comes from analogies. And in fact, I mean, I like to make an analogy to talk about the connection between my two talks, today and tomorrow. Today, since I'm in Chile, I will say that today my talk is about the Aconcagua of thinking, very tall, great thinking. And tomorrow my talk is about little tiny hills of thinking, everyday thinking, the ordinary kind of thoughts that we have. And so, now where did that thought come from? Where am I going? I guess I'm just trying to say that I was fascinated by these analogies, and I found that analogies were clearly guiding physicists, but they didn't want to talk about them. Later on, I became a cognitive scientist thinking about the mind and how thought works. And it took me a while, but I eventually came to the conclusion that the core, the heart of thinking is analogy making. And this is something that I've written about in a number of places, and particularly it's expressed most carefully in my most recent book, co-authored with a French psychologist, Emmanuel Sonder, a very close friend of mine, and Surfaces and Essences is the title. And in that book we talk about the centrality of analogy making in all of thinking, ranging from the foothills to the meager hills to the mountains to the very top, the very tallest mountains. And that's going to be the topic, the very foothills are going to be my topic tomorrow, but today it's the peaks, the great analogies. But let me tell you how I came to give this talk, not this particular talk, but talks about Einstein's analogy making in general. It came about in a strange way. In 2000, in the year 2000, I was asked by the physics department at Stanford University if I would give a talk in memory of my father. There is an annual series of lectures in memory of my father, who was a member of the physics department at Stanford and who died in 1990. And so in 2000, every year they give a Hofstadter lecture, and I was invited to give the 2000 Hofstadter lecture. And this was a big honor for me, and as a cognitive scientist who had once been in physics, I thought it would be beautiful to try to combine cognitive science with physics in some fashion. And so I gave my lecture the title, The Ubiquity of Analogy in Physics. Now, I don't know if ubiquity is a similar word in Spanish, but in any case, it means the total pervadedness. I mean, how to say it? Is ubiquity a good word? How do you say it in Spanish? Ubiquidad. Ubiquidad. Okay, the ubiquity, or the ubiquity of analogy in physics. And I gave my title, and I told them what the lecture was going to be about, but I wasn't too convinced that I was going to really be able to defend this title. I was a little scared. I thought, oh, I know a few analogies in physics, and maybe I can talk about those. And I distributed a flyer to all the graduate students and all the professors in the department, asking them to tell me about analogies that they knew. And then I also started looking for other little diversions, like poems about physics and drawings and humorous things, so that I could fill up my time, because I was worried that I'll find 2 or 3 analogies, and I really won't be able to prove that analogies are ubiquitous. However, over a period, I had months to prepare, and over a period of months, as I perused the literature of the history of physics, I started seeing one by one, over and over again, analogy after analogy after analogy after analogy. Not all of them were called analogies by the people who made them, but they were analogies if you looked at them. In other words, very often they were thought processes that if you really looked at what was going on, it was an analogy, but the person might not say that. And so I got rid of all the poems, and I really concentrated on the deep role of analogies in discovery in physics throughout centuries. And my lecture was extremely exciting to me. I will always remember that as being one of the great moments of my life. But there was a very, very curious thing about this lecture in 2000, which was nowhere did I talk about analogies made by Albert Einstein. Nowhere. And that's very peculiar. You would think that, after all, Einstein is in some sense the most famous of all physicists and perhaps the greatest of all physicists. And so why wasn't I talking about Einstein? Well, I think it was because I was scared of approaching Einstein's analogies, because I didn't know if there were any. It was the same exact fear that I'd had about the lecture in general. I thought I might not find enough material. And in Einstein, I had a special fear, because I thought, oh, this man was so intelligent that he probably didn't use analogies at all. He probably just reasoned everything out, did it all by equations. He just was so smart that he avoided analogies. When I look back on this thought, I have to laugh, because after all, it violated my own deep belief about thinking. My deepest belief about thinking is that at its base, it is analogy making. But I didn't have enough faith in my own self. I didn't really believe totally my own theory, and so I just avoided Einstein. I put him aside, and I had Heisenberg's analogies, and Dirac's analogies, and Poisson's analogies, and Niels Bohr's analogies, and Newton's analogies, and so forth, and so on. Many, many other people, but I avoided Einstein. Well, that was in 2000. In 2005, I was invited by the Library of Alexandria in Egypt to participate in the 100th anniversary celebration of Albert Einstein's Annus Mirabilis, 1905, when he published roughly 5 papers that were all fantastically insightful, important, revolutionary, and so forth, 1905. And so this was 2005, the 100th anniversary. And of course, I was very, very honored to be invited to participate in this celebration. I mean, there were many celebrations all over the world of Einstein's Annus Mirabilis, but this one I was invited to, and I was very thrilled. So I accepted, and I thought, okay, it's time to, if you know the expression in English, bite the bullet. And that means, it means it's time to face the truth. You have to now look for analogies in Einstein. And fortunately, a few months before I went to Egypt, a physicist came to my university, Indiana University. His name is John Rigdon. And Professor Rigdon gave a fantastic lecture on Einstein. And in fact, today's lecture by me is in many ways based on John Rigdon's lecture. But his lecture talked about one particular analogy that Einstein made that was very profound, very revolutionary. And it showed me in a crystal clear manner that indeed Einstein's deepest ideas did come from analogies. Yes, they did. And that gave me some confidence. And so then I bought a book that he had written, and I bought several other books about Einstein's thinking, the history of his thoughts, and so forth. And I read them from beginning to end, all of them. And I would note in the margin, analogy, here's an analogy. Here's another analogy. Here's another analogy. So I had a big collection of analogies by Einstein. And I came to realize that, yes, analogies pervaded Einstein's thinking just as they did everyone else's. It was only perhaps that sometimes analogies, Einstein's analogies, were more profound and in some sense more subtle than the analogies made by other people. Not always, but often that was the case. And so that was a great revelation to me, very important, and I gave my lecture in Alexandria, and I was very pleased with it. And then I gave it many other times in different places, and so that's sort of what I'm going to do today. But today I'm going to concentrate probably mostly on one particular analogy and the history of the history of Einstein's thoughts and the reactions to those thoughts, and we'll see. And if there's time after that analogy, I might do one or two more. It depends. But the main one that I want to talk about then is the analogy that gave rise to what Einstein referred to as his most revolutionary discovery ever, and which was not relativity, special or general. It was the idea that light is composed of particles. And that idea was one of his papers in 1905. And what Professor Rigdon in his lecture in Bloomington, Indiana in 2005 pointed out was that the impression that most people have, especially physicists, is that paper that I'm referring to, that famous paper, is about the so-called photoelectric effect. And it's usually referred to by people as the photoelectric effect paper. And that's really a bad misinterpretation of that paper. The real title of it involved the idea of the nature of light. And it was what is the nature of light? And the bulk of the paper, the majority of the paper, is devoted to a particular analogy that Einstein made that led him to the idea that light could be composed of particles. Let me first mention that, just to put a little transparency up here, that this idea, light as a wave, was, let me go back a little. In the time of Newton, there was a lot of dispute about the nature of light. Nobody knew what light was. And Newton thought light was made of particles, and some other people like Robert Hooke, who was sort of a rival of Newton's, thought it was waves, and Christian Huygens, a Dutch physicist, thought it was waves. And after a period of fight between the particle believers and the wave believers, in the early 1800s, there was a total resolution. That is, an English physicist named Young and a French physicist named Fresnel did a number of experiments that proved absolutely conclusively that light was a wave. That was in the early 1800s. And from then on, it was accepted. Then in about 1855, Maxwell wrote down the equations for electricity and magnetism. Now, those are things that nobody had any reason to believe were connected with light in any way whatsoever. But Maxwell saw that in his equations, his 4 equations, you could see what happens in vacuum when you look at the properties of electric fields and magnetic fields intertwined in some fashion. Maxwell was able to do the mathematics, and he solved the equation for electric fields moving through, electric and magnetic fields moving through vacuum, and he saw that those fields would propagate in a wave-like manner, sort of oscillating, and they would always propagate at a particular velocity, which he was able to calculate from some numbers that were in the equations. And that velocity, he calculated the number, and it came out to be approximately 300,000 kilometers per second. Now, that was an enormous velocity, but it also was a velocity that was known because of some experiments that had been done prior to that time in measuring the speed of light. And in fact, it was almost exactly the same number. In other words, what Maxwell had discovered was that electromagnetic waves had a natural speed which was the speed of light, the same speed as light. And all of a sudden, it seemed as if it was telling him that light consisted of electromagnetic waves. And of course, this supported totally the ideas of Young and Fresnel, and made it even stronger case that light absolutely was waves. Then in 1889, when Einstein was 10 years old, a German physicist, Heinrich Hertz, made some experiments to test Maxwell's theory about waves, electromagnetic waves being propagated. And he set up an experiment in which he was able to send a wave across a room and have it be detected at some distance, and electromagnetic wave. And in fact, his experiment worked. But he found out he needed to have darkness in the room. And he found out that the properties changed a little bit if he had lights on or if he put the curtains down. And this was just a small change in his experiment. He found it annoying because it made it harder to, it reduced the effect. If he put, darkness was useful, but it reduced the measure, the ability to detect the electromagnetic wave. So he was a little bit disappointed. And he wrote about this interference with his experiment in a separate paper. In other words, one paper was saying, look, I have discovered, I indeed have confirmed that Maxwell's prediction of light being an electromagnetic wave is true. There are electromagnetic waves that propagate at this speed, yes. But at the same time, he was saying, it's a little annoying because I have, found this disturbing effect. Well, this effect was called the photoelectric effect. And what is interesting is that although he had no idea, this was the part of the root of the destruction of the idea that light is waves. So in the same experiment, he was proving that light is waves and also undermining that idea that light is waves. But nobody knew that at the time. All they knew was there was this funny effect. Now, back to Einstein. So Einstein in 1905 made an analogy between two systems, and I think I'm sorry, maybe I should, I don't know, maybe we should, can you see this board, even in the back? I'm just going to draw a little picture just so that people can know a little bit what I'm talking about. I'm going to talk about two systems in physics. One is called an ideal gas, and one is called a black body, and I just want to tell you what they are. So an ideal gas, you probably know, but in case you don't, is essentially it's a gas that's contained in what they call a cavity. It could be a balloon, it could be a metallic cavity. It's just some kind of container. So the gas has a temperature, and it has a size, that is the volume of the container, volume and temperature and pressure, three quantities. How much pressure does it exert against the walls of the container? What is the size of the gas? And what is the temperature that the gas is at? Those three quantities. And so if I draw a picture of an ideal gas, I can say this is the container, and this is an atom, and this is an atom or a molecule, whatever it is. This is another one. And each of them, I'm going to attach an arrow to them. Each of them is moving around, and they can hit the wall and bounce back, or they can, two of them can hit each other. They can bounce off of each other. So that's an ideal gas. You have atoms or molecules in collision with each other, and physicists have studied the properties of ideal gases, or they had at that time studied the properties of ideal gases for a couple of hundred years. A lot was known about them. In particular, Maxwell, once again, and Austrian physicist Boltzmann, the two of them together, or not working together, independently, had found a spectrum for an ideal gas. Let me tell you what I mean by a spectrum. What that means is that when the gas has a given temperature, not all the molecules are going at the same speed. They're zooming around inside. I guess what you should do is make an analogy. This is a pedagogical analogy to a pool table. If you think of a pool table, so I have a pool cue, what they call a cue, a stick, and I hit the ball, and I make all the balls, 15 balls, at least in America, I don't know when you play pool here, but anyway, imagine about 15 balls, and I go, pew, and there's an explosion, and all the balls start moving around the table, banging into each other and banging into the walls, and just obeying the ordinary rules of Newtonian mechanics. So they have nice collisions and so forth. We can also imagine that there's no friction so that they keep on going forever. Once I put that energy into the system, they just move around, bang around, bang around. The point is, though, that not all of the balls are going to be going with exactly the same speed as all the others. Some of them will be going slowly, some of them will be going quickly, and when they hit each other, their velocities will change. One will add some velocity to the collision will add some velocity to one, take away velocity from another, and so forth. And so when you have only 15 balls, you can't do very much statistics with it, but when you have trillions and trillions and trillions of molecules inside an ideal gas, then you can ask yourself questions about the distribution of velocities. How many molecules are going at this slow speed? How many molecules are going at this little faster speed? How many molecules are going very fast speed, and so forth. And if you make a graph of it, it'll look something like this, just an approximate sense. I mean, it's a very simple idea. Now, what this graph means is this horizontal axis is speed, and the vertical axis is how many. So there is a particular speed, this particular speed here, that has the most, the peak. More particles or atoms are going at this speed than at any other speed. This is the speed that corresponds to that temperature. This is the maximum, most likely speed in an ideal gas at that temperature. There are other molecules that are going at lower speeds, and there are molecules that are going at higher speeds, but this is the most popular speed. Okay, so that is what we call a spectrum. That spectrum is what Maxwell and Boltzmann had calculated. And they had calculated an equation that gave the form of that curve, telling you how many molecules are going at each different speed. This is a very important discovery. And let me also point out, I mean, I'm under pressure of time, of course, but I can't give you a total history of physics. But I do want to tell you something which is really amazing. In the 1800s, of course, the existence of atoms was extremely controversial. It was fantastically controversial, and many physicists and most chemists, I believe, did not believe in atoms at all. And yet, in the roughly, I don't remember the years, 1860, 1870, both Maxwell and Boltzmann had the courage to assume that ideal gases, or gases in general, or things in general, were made of atoms indeed, and they went ahead and made these calculations without, in some sense, having a proof that atoms existed. There was no proof that atoms existed. Now, we move fast forward a little bit to Einstein in 1905. I'm not going to talk about his paper about atoms in 1905, except to mention that he made another revolutionary contribution in 1905, which was a paper usually called the Brownian motion paper, that effectively convinced almost all physicists and chemists that atoms did indeed exist. And how he did that, I'm not going to explain. But I just wanted to say that as late as 1905, there was enormous doubt in many physicists' mind about whether atoms existed, let alone what they looked like. Nobody had the foggiest idea what an atom was, but just whether they existed was even a question, a big question in 1905 still. So, so Einstein was aware of Maxwell and Boltzmann, and Einstein was a big believer in atoms. As I said, he wrote a very, very important, almost the final paper, the last word on the question of whether atoms exist or not in 1905. Now, I want to talk about one other system that he made an analogy to. So that I have to erase this one and talk about another system. I'll leave the graph up because I'm going to use the same graph, basically. I'm going to talk about the spectrum of a different system. This other system is called a black body, and for various reasons. But the idea is that here you have a cavity, once again, or a container, but it doesn't contain particles, or at least people would have said up until then that it did not contain particles. They would say, this cavity is filled with electromagnetic waves. In other words, what we're going to do is we can shine light in, for example, and the light will bounce around against the walls, and we'll have, actually the way that you create a black body is not by shining light in. The real way, if you have an electric stove, you know that when you turn it up on high, the burner, which starts out black, starts getting sort of orangish color, and it can get sort of orangey when it gets very hot. That's really what a black body is. It's you heat something up and light starts coming out of it. And so imagine that you heat up this container and it starts glowing inside, so that what it means is that electromagnetic radiation is bouncing around inside the container. But not all the radiation is of exactly the same color. It's not all just one color. There is radiation that is red, there's orange, there's yellow. I'm following the rainbow spectrum of red, orange, yellow, green, blue, indigo, violet, and so forth. And other, ultraviolet, infrared. There's radiation of many different frequencies. And then the question is, if I heat this up at a given temperature, let's say, I don't know, 500 degrees Fahrenheit or 300 degrees Celsius, whatever you want. It doesn't, don't care about the number. If I heat it up to a particular temperature, how much light is there of different wavelengths? Okay. And so the graph that I just drew there is, can be used for that. So if this horizontal axis now is wavelength, and this is how much energy there is at that wavelength, then it's saying there is a particular wavelength at a given temperature that is maximal. It means that, so that, for example, at a low temperature, just to give you a simple, I mean, actually, I have never really watched this on my stove, so I can't tell you, but if I heat it up at a low temperature, I don't get much color. But if I put it on high, it gets very bright. But the transition of color is hard to say. But the point is, you've heard of stars that are blue, right? Or, blue, what are they called? There must be some term, official term. Anyway, there are stars out there of different colors. And it's because they're at different temperatures. The hotter you get, the more, the shorter the wavelength is at the peak. So I don't want to go into all this in detail. All I want to say is that I didn't draw any picture for the waves bouncing around. I don't know quite how to do it. If you think of waves in the ocean, when they approach the beach, they're straight lines, right? They're coming toward the beach. They're straight lines with a certain distance between them, maybe 50 meters or maybe 100 meters. But one will come in and break on the beach, and then another will come in, and another will come in. So that sort of thing, I'm going to represent waves like that. So here is an electromagnetic wave that's moving along, like that. And here's another one, but I'm going to draw it with a slightly different wavelength, a little shorter wavelength, and this one is moving that way. And then I'll draw one last one with a longer wavelength. The distance between things is a little larger. This is a messy picture, excuse me. So, but this is just the idea that I have waves inside this cavity that come from the fact that the cavity is heated up. So, and it has that distribution. Now, Einstein took a look at that spectrum, and he took a look at the Maxwell-Boltzmann spectrum for the ideal gas, and he said these are very reminiscent. In other words, there is an analogy between these systems. Now, that didn't lead him to the idea that light was composed of particles. What he did, though, was he wanted to see how this analogy, how deep this analogy was. And so he did some calculations to compare the formulas that describe the behavior of these two systems, the ideal gas on the one hand and the black body on the other hand. And for the physicists here, I'll just say that he calculated, to be very technical, entropy fluctuations. I don't want to go into that, but just in case you're interested, he did some calculations of the entropy fluctuations of these two systems. And in the equations that he got, for one, I'm just going to write down one little thing. In equation for the black body, somewhere in that equation for the entropy, there was the letter N, which corresponded, which denoted the number of particles, the number of molecules in the system. How, if you think of it as a pool table, how many pool balls are there on the table? Just the number of entities that are bouncing around in the ideal gas. That's in one of the equations. In the other equation for the black body, in exactly the counterpart place, in other words, the analogous place, there was this expression. Can you read that? E divided by h nu. Nu is a Greek letter, and it means the frequency of the, basically, it's related to the wavelength. H is a constant. It's just Planck's constant. You can almost ignore it, but if you multiply h by nu, you get a very small energy, that's all. It's an energy. And capital E is the total energy of the system at that wavelength. This ratio corresponded to that number n. Now, Einstein thought about this because the two equations for the entropy fluctuations of the two systems were identical, absolutely identical, except that one said n and the other said E divided by h nu. Other than that, they were exactly the same equation. And Einstein said that must mean that this quantity is acting like it's telling me that there's a number of things there. And how many? It's E divided by that, this big energy divided by that little energy. It's telling me the energy of the light comes in little chunks of this size. This many, the number of chunks of this size in this would be that ratio. And that's telling me that effectively the light in the, or the electromagnetic waves in the container consist of little chunks having that much energy. Now, this was a completely wild thought. It totally ran against everything that all physicists had believed ever since Young and Fresnel in the early 1800s, and especially after Maxwell and the confirmation by Heinrich Hertz's experiments. It completely ran against everybody's belief, totally. Einstein said at the end of his paper, he gave three little appendices, you might say, after having suggested that light might be composed of chunks of that size, h times the frequency, Planck's constant times the frequency. He said, there are three ways I can think of to test my hypothesis. And he listed them, and I'm not going to list them, but he did. 1, 2, 3. And this is sort of an appendix to his paper, sort of saying, I've set my idea out here, light consists of particles, by an analogy, but now here are three tests, possible tests. And one of them was talking about the photoelectric effect that Hertz had discovered. He said, if my idea about particles is correct, I can predict certain things about the photoelectric effect. He didn't know how the photoelectric effect would behave. Nobody knew at the time the details of a photoelectric effect. It was too hard to measure. So Einstein made a prediction about the photoelectric effect based on the idea that light was particles, not waves. And nobody believed him. He published his paper in 1905. Nobody at all believed him. And when I say nobody, I mean literally nobody, except for one person, namely himself. And they mocked him. And then in the subsequent years, Robert Millikan, an American physicist, made very, very precise measurements of the photoelectric effect in the years 1910 to about 1915. And he verified or confirmed Einstein's predictions 100%, absolutely perfectly. And in 1916, Millikan wrote a book summarizing the results of his experiments. It was a famous book. It won him the Nobel Prize for physics, his work on the photoelectric effect. And in it he said, I have confirmed the predictions of Albert Einstein, but we know very well that the ideas behind his predictions make no sense. So I've not confirmed his ideas that light is particles. I confirmed his prediction that came out of that, but certainly light is not particles. And he said even Einstein has abandoned the idea, which was totally false. Einstein had not abandoned the idea. And, but it's amazing that he would have said such things. A few more years passed. Still nobody believed. In 1921, as I recall, Einstein was awarded the Nobel Prize for Physics, and the citation was for having, it's a very blurry, ambiguous citation, but it says something like, for having predicted the behavior of the photoelectric effect and other contributions to theoretical physics, like special relativity, general relativity, and a million other things, which they refused to talk about. But they said he predicted the behavior of the photoelectric effect. They did not say because he said that light was composed of particles, because still nobody believed it. In 1922, Niels Bohr was awarded the Nobel Prize for Physics for his work, and he gave a talk in which he mentioned Einstein's ideas about light and said they were worth nothing. 1922. In 1923, an American physicist named Arthur Holly Compton discovered a strange effect in which light bounced off of certain particles and came off with a changed wavelength, which was completely against Maxwell's equations, completely against the idea that light was waves. And he published this, and it was confirmed, and all of a sudden, the Compton effect, everybody changed their mind. Overnight, the whole world believed that light was composed of particles. In 1923 or 24, that's about 18 years after Einstein's idea in 1905. It took 18 years for the idea to, and then 3 years later, an American chemist named Gilbert Lewis gave a name to these little chunks of light, photons, and that's what today we know. And I noticed today, or yesterday, we were driving around in Santiago, and I noticed that I think there's a car called a photon, isn't there? I mean, it's so common today that we just throw it around as if everybody, of course light is made of photons. Everybody knows, it's just a cliche. It's very interesting. It's very interesting how these ideas that are so profound in their content, it took 18 years for the world of physicists to even believe in them at all. And now, of course, light's made of particles. Well, I want to just conclude with a kind of an amusing picture that I once drew that alludes, if I can find it, that alludes to what Francisco was talking about at the beginning of my ambigrams. I'll put a little thing here. So I don't know if you can read this, but if you kind of squint a little bit, it says light is a wave. And if you look at it in more detail, it says light is a particle. And nobody to this day really quite understands the nature of light. Einstein said very close to the end of his life, I've worked for 50 years trying to understand what light is, and I still don't understand it, and so on. Well, I'm sure I've run out of time. I haven't looked at my watch. I'm probably way over time. But let me simply say that there are lots of other analogies that Einstein used in making his deep discoveries. I've talked about the so-called photoelectric effect paper. But what I want you to remember is the photoelectric effect paper is not about the photoelectric effect. It's about an analogy between an ideal gas and a black body. That's what it's about. And it leads to the idea that light is made of particles. And as an appendix, he says how to test it. And he makes a prediction. But that's just like an appendix. It's not the photoelectric effect paper. Yes, it predicted it. But because the Nobel Committee was so timid, and they gave an award to him for this paper, but they gave an award to him for the appendix, not for the main content of the paper, which was the deep part. So, as you know, Einstein, where are my glasses? Here. Einstein made many, many other deep discoveries, important discoveries in physics, and I don't have the time to talk about them, but I do want to at least give my own little homage to Einstein. And in doing so, I'm going to do it through poetry. And Einstein loved writing little jingles, a jingle being a short, little trivial poem, kind of like in advertising. Einstein loved to write little poems. He wrote poems for his friends' birthdays, as I do. I write poems for my friends' birthdays often. And, but mine are longer. Einstein usually wrote four-line poems. And here he's writing a poem about Newton, and he celebrates Newton's genius. And I took this poem. I'll give it to you in German, in Einstein's original German. I took the poem and I translated it in English, but I substituted Einstein for Newton. So I want to share this with you as a conclusion to this lecture. It refers to other discoveries of Einstein, not to the photon discovery, not to the light is particles discovery, but you all know about Einstein's other discoveries, at least you've heard of them, special relativity, general relativity, and things having to do with cosmology and how the cosmos is constructed and so forth. So here is the original poem that Einstein wrote in 1942. I don't know if it was celebrating something about Newton, maybe it was, but anyway, let's read it in German and then I'll translate it into English. So, seht die Sterne, die da lehren, wie man soll den Meister ehren. Jeder folgt nach Newtons Plan, ewig schweigend seiner Bahn. Okay, it's a beautiful, actually it's a lovely poem about Newton and his predictions of how the stars move in the cosmos. So I'm just going to simply give you a translation, but Einstein is replacing, other than that, it's the same poem in English. So here's my version. In 2005, I read this at Alexandria, Egypt. Alexandria, Egypt is AE, by the way, just as is Albert Einstein. AE. So my title today is Albert Einstein Extraordinary Analogizer, AEEA. There it included Alexandria, Egypt, so I had another AE. So, see the stars above whose blinking brings us awe for Einstein's thinking. He foresaw how each would swerve, silent in its endless curve. Thank you.